Let's suppose we have a surface that's given by the graph of a function. So the graph of a function in three-dimensional space. So the idea here is that this function, the domain of this function might live downstairs in the xy plane. So I'm just going to draw a nice little domain here, just for the sake of the picture. But let's say this is the domain, so that's the D in the graph, and the surface itself is given by the graph of this function f of xy. So we know how this works. This idea works. The function f takes points in the domain and it assigns height to them, and so every point upstairs on the surface has coordinates x, y, f of xy. And what we'd like to do now is compute the surface area of this surface by regarding this surface as a parametrized surface. So we've already talked about how to compute the surface area of a surface given by a function back in chapter 15. And if you remember, what we did was we chopped up the surface into small pieces by taking basically small pieces of the domain down below and then approximating by tiny pieces of the tangent plane and computing their surface areas and adding them all up, making a Riemann sum argument. And if you're thinking that sounds very familiar to what we've done with the parametric surfaces, then you're exactly right, and that's what we're going to do right now. So the idea here for the graph of a function f of xy in terms of the parametric sense is that instead of regarding this function as a regular function of two variables, from the domain D downstairs, we're going to regard this as a parametric function. And how's the parametric function going to work? Well, it's going to still take in these points that live downstairs in our domain, and it's going to assign to the output point the exact same x and y coordinate. So x comma y. But then what does it do for the z coordinate? Well, that z coordinate is given by the function f, okay? The actual function f here. So now that we have this parametric function, in reality, what are we doing, right? We are, in our minds, pulling out the domain from this picture and just kind of rearranging it as its own little domain over here in our parameter space. So our parameter domain is another copy. You can think of this as a different copy of the xy plane. And then the function f, or the function r in this case, maps all the points in the parameter domain to the surface over here. And so it traces out this surface as a parametric surface now. Okay, so that's the idea, and what we'd like to do is compute the surface area now, right? So we know from our previous studies from this chapter that the area of a surface is given by the double integral over that surface of 1 ds, where this is a capital S, surface area element. But when your surface is parametrized, what we can do is pull back our integral along the vector function r and actually compute a nice integral in this domain D, the parameter domain over here in two-dimensional space, and it ends up being the double integral over the parameter domain D of ds. So the formula for ds is that it becomes the length of the normal vector, length of nu, dA. All right. So, and recall here that nu itself is the cross product, right, of the derivatives of r. So with respect to the parameters, and the partial derivatives of r with respect to the parameters, in this case the parameters are x and y, so this will end up being the partial derivative of r with respect to x, cross product with partial derivative with respect to y of r. And then we'll have to, of course, take its length to compute the surface area. So let's do this. As we said, our r, the formula for r, is just xy in the xy components, and then the function f of xy in the third component. And we need to compute the partial derivatives of this with respect to the two parameters. So r sub x is dx dx, that's 1, right? dy dx is 0. X and y are both independent variables here. And then I'm going to drop the of xy here, but this is going to be the derivative of f with respect to x, the partial derivative of f with respect to x. And we're going to do the same thing with our y partial derivatives. This time it's 0 in the first component, 1 in the second component, and then df dy in the last component. And to get our vector nu, we have to take the cross product of these. So we get a vector back. The first component of the vector is going to be 0 minus df dx. Okay. Second component is 0 minus df dy. And the third component is 1 minus 0. All right, so that's our vector nu. But remember, when we integrate up this vector function to find the surface area, we need the length of nu, right? We need the length of nu. And the length of nu squared, all right, is just the sum of the squares here, right? So I'm going to rearrange this and write this as 1 plus df dx quantity squared plus df dy quantity squared. Okay, and when this goes into our integral, we need to square root both sides, right, to get the length of this thing. And what we find then is that number one, our ds, our surface area element, which is always equal to length of nu dA, this is just equal to the square root of 1 plus df dx quantity squared plus df dy quantity squared times dx dy. This is dA, so it could be in any order you want right there. And then if we're going to integrate up our surface area, what do we get? Well, it's just, remember, integral of this over the region, right? The domain d, the parameter domain, which is just the domain of the function f to begin with, of this square root. 1 plus df dx quantity squared plus df dy quantity squared, all under the root, times, I'll leave it as dA, but dx dA. So that's the surface area of a surface that's given by the graph of a function.